Now let's learn how to factor out the GCF from a polynomial. I just said the word factor. What does that mean? Factoring means take an algebraic expression that's written as addition or subtraction of terms and rewrite that into an equivalent algebraic expression that's written as the multiplication of two algebraic expressions. So for example, on the left side, written as a list of terms added or subtracted, I have this polynomial. Now, if I want to factor that polynomial, I can rewrite it like I have on the right-hand side. On the right-hand side, it's not written as a list of terms added or subtracted. It's written as the product of two algebraic expressions, the product of this times this. Now, you may notice there's addition and subtraction inside of the second factor, but that's at the next level. The first level that you come to is this multiplied by this. So this is written as the product of two algebraic expressions. The individual expressions are allowed to have addition and subtraction in them, but the thing that makes it factored is that the first level is two algebraic expressions multiplied together. Now, a critical piece of this is that the two ways of writing the algebraic expression must be equivalent, must be equal to each other. If I write the algebraic expression in this format as an addition or subtraction of terms, or if I write the algebraic expression in this format as the product of two other algebraic expressions, it doesn't matter. They have to be the same. They have to be equal. How do we know if this expression is equal to this expression? Well, we could multiply or distribute. So take this 3, distribute it to every term, and you would get exactly this polynomial. So this proves that these two are equal to each other, but they're written in different formats. So in this case, we're concerned with the process of factoring. The process of factoring means taking an expression that's written in this format as a list of addition or subtraction and rewrite it into this format, a product of two expressions. But you can always check your factorization, and you always should check to make sure you did not make a mistake, by taking the factored form, multiplying or use the distributive property, and it should take you back to the unfactored form. Okay, so that's what factoring means, and it's important to have an understanding of what factoring is. If you were asked to factor an algebraic expression, or in particular a polynomial, you can use this flowchart to guide your thinking through the process. The first step is always to factor out the GCF. From there, you can move along this flowchart. Our objective is to learn how to perform the first step, factoring out the GCF. You should always do this step before you proceed with the remaining parts of the flowchart. So how do you do the first step? The first step in factoring out a GCF is to find the GCF. Now, I discussed this in a previous video, so please refer to that previous video if you need help with the first step. The second step is to factor out the GCF. Well, how do you do that? Here's the steps. Let's go through an example to see how these steps work. In this example, we're asked to factor out the GCF. Here's the steps we just discussed. The first step is to find the GCF of all the terms. What are the terms? The terms are the variable expressions separated by a plus or a minus. So we have three terms for this polynomial, because these are the parts that are separated by a minus or a plus. So what's the GCF of these three terms? The GCF is 3x. Again, if you need help with that, please refer to the previous video. Now we go to step 2. The first step is to make a new set of parentheses. I went ahead and drew a line representing each of my three terms from the original polynomial. However many terms you started with is however many terms you're going to have on the inside of your parentheses. So I like to go ahead and draw those lines to represent the spots I need to fill in. The next step is to write the GCF on the outside of the parentheses. The GCF is 3x, I put it on the outside of the parentheses. Now take each of these three terms from the starting polynomial, but we need to divide each of them by the GCF of 3x. Remember how I put a line for each term that was on the inside? Here's my three terms. I take each one of those, put them into their spot, represented by that line, but then I have to divide each of these terms by the GCF. Now finally, let's simplify each of these. The first term on the inside simplifies to 2x squared. The second term simplifies to minus 3x. And the last term simplifies to 4. Now for the second term we have plus a minus, which is just simply minus, so we can simplify that. Now everything's fully simplified, so this is our answer. We've factored out the GCF. Thus, we've written this polynomial into its factored form. So the polynomial in unfactored form is here, the polynomial in factored form is here. Remember, factored form means it's written as the product of two expressions, this expression and this expression. Unfactored means it's written as the addition or subtraction of multiple terms. In this case, it's this term minus this term plus this term. Remember that we discussed both of these forms must be equal. We can go back and forth between these two forms by either factoring or distributing, multiplying. So if we're in the unfactored form, we can go to the factored form by factoring, which is what we did. But once we're in the factored form, we can go back to the unfactored form by multiplying or distributing. It's really important to understand this concept because this helps us check our answer. Knowing that these two forms must be equal, we can take our answer, which is the factored form, and multiply it out to see if it's equal to the unfactored form. If it is, it means our answer is correct. If it's not, it means our answer is wrong. So let's do that. Let's check our factorization by multiplying the factored form. To multiply these two polynomials, we have to use the distributive property, which tells us to multiply the 3x by every term from the second polynomial, which gives us this, and simplifying each of these products results in this. Now remember, the factored form and the unfactored form must be equal. The factored form we just proved is the same as this. Now the question is, does this equal the unfactored form? And the answer is yes. Therefore, we've shown that our factored form is correct. So whenever you factor, it's always a good idea to unfactor, which means multiply out, and it must equal the unfactored form. If it doesn't, your factorization is wrong. With factoring, it's really easy to make a simple mistake, so it's really important to always go back and check. When factoring out a GCF, the inside polynomial will always have the same number of terms as the starting polynomial. For example, we take this polynomial has two terms. When we factor out the GCF, there's still two terms inside the parentheses. This would be incorrect. There was two terms in the starting polynomial, but only one term on the inside. So remember this as a way to quickly check if you're on the right track with your factorization. Let's do a concept check. Which factorization of this polynomial is correct? This is the correct one. Why is that the correct one? Well, if you distribute 3, it would equal the starting polynomial. So what's wrong with the other options? Well, option B has the correct inside, but it's missing the GCF on the outside of the parentheses. If you don't have the GCF on the outside of the parentheses, then there's nothing for you to distribute when you check, so therefore this does not equal the starting polynomial. Remember, that's how you know if factorization is correct. The factored form must equal the starting polynomial if you were to multiply it out. For the option from part B does not satisfy that, so it's wrong. What about part C? It's got the GCF on the outside, that's good. But look at the inside, only 2 terms. This polynomial started with 3 terms, so we automatically know C is wrong because there's only 2 terms on the inside. Let's do one more example. Factor the GCF from this polynomial. First, let me ask you a question. Is this polynomial in factored form or in unfactored form? It's in unfactored form. Why? Because it's written as 2 terms being subtracted. Remember, terms are whatever algebraic expression are separated by pluses or minuses. Because there's a minus in between these two, it's not factored. If there was a multiplication in between these two, then it would be factored. But in this case, it's a minus, so it's unfactored. Okay, so let's factor out the GCF. Remember the steps. Find the GCF, then factor it out. This polynomial has 2 terms, so we need to find the GCF of those 2 terms. Now, as we learned in the previous video, we can separate this into like bases. Think about what's the GCF of the numbers, i.e. the coefficients. What's the GCF of the base with a y? What's the GCF of the base with x plus 2? Separated each of those out. First, let's find the GCF of the coefficients. The first term has a coefficient of 6. The second term, we don't see a number in front, which means we know the coefficient is 1. So what's the GCF of 6 and 1? Anytime one of the algebraic expressions is a 1, the GCF is automatically a 1. Now let's look at the like bases with a y. The second term has a y to the first power. The first term does not have a y. That's why I put a 1 here. So I could add a 1 to represent the spot where a y may have been for the first term. Or remember, anything to the 0 power equals 1, so you could write this as y to the 0 power. So what's the GCF of y to the 0 power and y to the first? Well, remember, when you have like bases, the GCF is the base with the smallest exponent. Smallest exponent is 0, so the GCF is y to the 0. But y to the 0 is just 1, so the GCF is 1. Remember, anytime one of your terms from the list that you're trying to find the GCF of, anytime one of those terms is 1, that means the GCF is automatically 1. Let's look at our last pairing of like bases. From the first term, we have an x plus 2 to the first power. Remember, if you don't see an exponent, the exponent is a 1. From the second term, we have an x plus 2 to the first power. Now, you may be wondering, this looks a little bit more complicated. We covered a situation like this in the previous video, the video on finding GCFs. It doesn't matter that there's an x plus 2 instead of just like an x. This is all one base because it's inside the parentheses. So our base from the first term is x plus 2 to the first. Our x plus 2 from the second term is x plus 2 to the first as well. What's the smallest exponent? Well, they're both a 1, so the smallest exponent is a 1. Therefore, the GCF is x plus 2 to the 1, or more simply, just x plus 2. So we found the GCF for each of these pairings. Now we multiply all these individual GCFs together to get the GCF for the entire polynomial. Now, this GCF is 1, this GCF is 1, this GCF is x plus 2. We multiply those together to get the GCF for the entire polynomial, which simplifies to x plus 2. Okay, we found the GCF. Now, let's factor out the GCF. Remember how we do this. Make a new set of parentheses, write the GCF on the outside of the parentheses, write each term from the starting polynomial on the inside of the parentheses, divided by the GCF, and then simplify those divisions. Here's those parentheses. I have two terms in the original polynomial, so I put two blanks to fill in those two terms on my inside of my factored form. The GCF is x plus 2, so I need to write that on the outside of the parentheses. Now, don't be confused by the fact that the GCF has parentheses. That's fine. That's separate from the additional set of parentheses we had to add when we performed the factoring step. Now we have to write each term from the starting polynomial on the inside, but divide it by the GCF. Now we just need to simplify each of these divisions. In each case, the x plus 2 will cancel. From the first term, we're left with a 6, and from the second term, we're left with a negative y. We still have two terms left on the inside of this polynomial, as we said we should, since the starting polynomial had two terms. So this is our polynomial in factored form. It's factored because we have one algebraic expression multiplied by, remember there's implicit multiplication in between here, the second algebraic expression. Now remember, these two different forms must be equal to each other. Let's check our factorization by multiplying or distributing the factored form, and it should equal the unfactored form. We multiply by using the distributive property, distributing the x plus 2 to each term, which gives us this, which is exactly equal to the unfactored form, which verifies that our factorization was correct. Let's do a concept check. Is this polynomial in factored form? Yes, because in between each of these algebraic expressions is multiplication. So what are the factors? 3, x minus 2, and 4x plus 1. Is this polynomial in factored form? No, because in between these expressions is a plus, not a multiplication. Therefore, these are terms. So we have two terms, not factors. Now, in each term, yes, there's multiplication, but that's the second level. The first level that we come to is this plus this. Because it's a plus, it's not factored. Is this in factored form? Yes, because there's multiplication in between here. What are the factors? 3 and 4x plus 1. In this video, we learned how to factor out the GCF from an algebraic expression.